Hello everyone, welcome. How are we all doing? Right, much better. How's everyone doing? Welcome. Hope we're all having a good week. Just gotta put it on chat only on my phone. There we go. Much better. So now I can see what's going on in the chat. So, last stream we got virtual memory working. It's not fully tested, but it supposedly will run on Windows and the Unixes, right? Well, actually, not technically Unix, but just Linux, right? But anyway, so yeah, there hasn't been much that's changed, right? We're doing core engine stuff, so there will be nothing visual going on for the next few streams. So the next thing we're going to work on is a way to allocate some memory at runtime. But we want to make sure that any of our allocations are fast, right? We don't want to make a call out to the operating system in a frame. We want to pre-allocate. Ideally, we want to pre-allocate all the memory that we're going to be using, so our threads don't get blocked by calling out to the operating system. So yeah, a good idea would be to probably implement the most fastest and the most simple allocator. So we're going to pre-allocate a chunk of memory with the virtual memory stuff we made last stream, and then we're just going to bump allocate from there. So let's take a look at our directory structure for a minute and just figure out what we want to do. So I've got this core thing, but all the other things are in a folder, and I think we should move it into a folder, right? Because yeah, this is not good. So because they all of them have their own folders, even the OS, right? So yeah, just help keep stuff clean. These are like sub modules, should we say? So we're going to do a git move. Well, let's first do a git pull. What about with the tags? Where's all the tags? Wait a minute. That's all good. Okay, so everything's up to date. That's good, because I did some work on Windows to get the virtual memory stuff working. And what we want to do is do a git move now. Git move source core underscore, not really core underscore. Yeah, core underscore shared into core, source core slash, right? That's moved into there now. Right, I'm going to do the same thing again, but this time dot star, and there's core H and core C. So we need to go through all of our files now and quickly just change out all of that. So we're just going to do a super nice grep. So open up this new terminal here. Do a nice grep. Hey there, Not So Red, how you doing? How's it going? Yeah, I'm doing okay. So I drank like tons of Coke over the weekend, and it just started catching up with me yesterday. And I got such a sore throat and like, you know, too much caffeine. But it was really nice on a warm day, you see. So I'm feeling a bit, I can feel when I move my eyes quickly to left and right, like on the eyes, like a bit of eye ache. And a little bit drained as well at the same time. Yeah, so other than that, everything is going awesome. But yeah, that's just, yeah. the price I pay for eating all those Cokes. No, drinking all those Cokes. Hey there, Rohan. Yeah, allocator time. We're just gonna start off stupid simple though, you know? But yeah, it's gonna be awesome. I don't know how how to regex. Is it plus? Alright, that'll do it. That's all I need. So where we include all these guys, we just need to do a bit of a refactor. Vim source main. Core. That's alright, we'll get there in a sec. OSH. Core shared. You're playing around with assembly this week. Awesome. You said to write a whole assembler before, right? Yeah. So if you want to learn assembly, the best thing to do is apply, make a very simple CPU. Just take a look at how x86 works or ARM works. Perhaps do both. That's what I did. So you're learning both of the assemblies and make your own sort of one out of that and see how they work. And if you write your own, you can write a little virtual machine for it and have something that runs, and write a custom assembly file that you'll handwrite the stuff in, the program in, and then run it in write a assembler which compiles that into the bytecode, and then run that through your VM. And the reason why I suggest it is because x86 and ARM are very complicated, so you can write a more simplified version. And you also get to take a look at both of the assemblies and how they work and kind of that sort of thing. Well, there is 6502, yeah, but it is very restricted 6502. There's limitations on that. But yeah, definitely. That's another way to start too. Yeah, you could just write a 6502 VM, right, and just run that. I'm sure that's not too difficult. And then, yeah. But yes, it's a really good way to learn to get some hands-on experience with it, you know. Because you get to see what's the way of saying it? You get to see how the tools work as well as yeah. Essentially, you just get to see how the tools work as well as simplify it to be a. No worries. What's this thing? I'll take a look in a second. Right, core/core. Excellent. Right, any more we're missing? OS. Right, definitely the Vulkan side of things. Source GPU, GPU Vulkan internal. GPU internal we mean. Is that right? Oh, okay. Right, I think that might be it. Should we give that a go? Scripts, let's run the script. And doesn't work. So GPU shared. Okay, there we go. So we just give that a quick run. And it still works. Cool, so we just commit that because we've made some form of move, and it'd just be good if that was isolated from what we're about to do next. So let's do a get, I guess add dot. Yeah. So we're just saying move core files into the source core directory, right? We just roll with that, and bam. So the next thing I want to do is actually open up those files and we wanted to start writing these custom allocators and things like this. So all right, what's this link about? UF trace. Interesting. Yeah, that's why I'm not going to try and write an assembler and disassembler. Oh, that's why I'm trying to write a disassembler and assembler. Good way to learn about this stuff. Yep. Yep. Like you can write an assembler in a single pass, by the way. You don't need to do multi-passes, so you can literally just scan over it. And you can read it like you can read over the string, and for every time you come across something, you can basically directly turn that into your machine code, right? And this thing isn't loading for me. Is it because of the dark mode? Yeah, it's not loading. Maybe I need to run it in another browser. Try Firefox. Do I have I have Firefox actually. Funny how like a Chrome-based browser doesn't work. Waiting for remark.js.com. So it's like they've got the JavaScript dependencies being like they're remote. Yeah, maybe you've got a cached dependency, maybe. Oh, it's coming. The function graph tracer. Graph tracer. Okay. Run the command. Then you can run that through. Oh, so it will see how long your stuff will take, maybe. Yeah, so there is perf, right? So is this like perf in a way? But you can see is the UI nicer maybe? Yeah. I wonder how it'll look with big lines of code, you know, will it print out a lot of stuff? Yeah. Yeah. Maybe that's nice because you can actually just view the you can find all the places in your code as opposed to using perf and having to. But then again, with perf, you see everything sorted from top to bottom, right? On what's the slowest thing. But then again, yeah, that's interesting though. Yeah, to see return values, that's interesting. That's pretty cool. How ready is this thing? Yeah, so it's like the trace stuff, but for user space, right? Right, and you can do the report thing. Yeah, this is definitely like perf, right? Cool. Well, um, what's it called? UF trace. Yeah, maybe I'll take a look at it at some point. I'll keep it in mind when I do performance stuff, but yeah, I just use perf right now. Or you can do do the timestamp stuff in your program, Right. So let's get to this linear allocator business. So as we said earlier, last stream we wrote a virtual memory system. Well, virtual memory, a way to reserve and commit virtual memory. So, excuse me. So it is the lowest level way of retrieving memory from the operating system, but we don't really want to call this every frame. We might want to call it on some threads maybe, but you don't want to run it on like your main threads usually, because you want to reduce the amount of system calls you do when you have a game, right? So what we want to do is want to pre-allocate a slab of memory and then have another allocator which uses that slab of memory that we've got from the operating system and gives it out to something that wants the memory. So the most simplest allocator is called a linear allocator, and we're just going to implement that because it's the simplest and the fastest one, and if we need anything more specialized we can just make it. So let's go to Milton quick. So the idea is we'll allocate maybe like 8 megabytes or something like that, right? And we'll have this allocator, or we'll have this piece of memory from the operating system. We've got 8 meg. It will possibly show up in the system. Well, maybe not, because you might have to actually start using it. But yeah. So what happens is we're going to have like a pointer here, which represents the start, and we'll have a pointer here, which represents the end. And every time we allocate from this allocator, we're going to advance a pointer, right? So there's 3 pointers. There's start, end, and the current position. So every time you allocate, you give that memory to the thing that requested it, and then you advance it. And the next time you allocate, you align this pointer to what the requested alignment, and then you advance it to where it needs to be. And then this is where it goes now. And then this range of memory from here to here goes out to the thing that just allocated that memory. So this is the quickest way to allocate memory because you're simply just adding like 2 integers together and doing some checks. So one powerful thing about this allocator is, so you might be thinking, well, what happens if you get to the end, and how do we prevent it from getting all the way to the end? Because if we're going to be allocating like this, we'll sure to get to the end at some point, and then we can't, reclaim any memory. Right? How do you reclaim memory if you're just advancing this pointer? Well, there's 2 ways you can reclaim memory. Well, how you reclaim memory is that you essentially, when you know that none of these resources exist or none of these allocations exist anymore, you can basically free the whole thing back to the default thing back here. Or you can actually, when you save you have allocated this thing out, you could back this pointer up and you can just store it on the stack somewhere. You can go into a function, do some more allocations, right? And maybe you allocate that thing and maybe you allocate this thing. But then what you can do is so you've come out the function now, and what you can do is you can just restore it back to this state instead, right? So effectively this really leverages stuff with a lifetime which is measurable. And when you program your application, you know the lifetime of the objects that you have. Maybe something needs to be more dynamic and we'll have a different solution for that. But typically we're going to have stuff that's either short-lived or statically allocated once. So another thing that this allocator could be used for is when you start up the application, we're going to have a static linear allocator, and this one never frees. So we just bump allocate all of the stuff we need, which lives for the lifetime of the application. And then we never free it, and everything just stays coupled together in this region of memory, all the static stuff, and it never gets freed until we shut down the program, right? So there's two ways this allocator can be used. So we can use it for static stuff and then also frame lifetime. So probably per thread, when we have threads, we'll have one per thread for a frame, and that's our temporary allocator, and it gets reset every frame and has some optional freeing on it. So yeah, if anyone has any questions about what we just went over, please ask, because we're going to go and implement this thing now. But this is how all of our things are going to get allocated is with this one allocator for now. But in the future, we can add more. Hey there, Bassandra, how you been? Yeah, I'm okay. Like, other than the fact that I'm ill because I've drunk too much caffeine over the weekend and it's just catching up with me, I'm doing really good. How are you doing? It's been a while. So linear. So right. Yep. Let's write the linear allocator first. So we're going to type def sum structure, right? Core linear allocator. Now I like to shorten the word allocator because it's going to be used in a lot of places, and everything stuff just gets very wide. But yeah, you know, everyone has a different way they shorten things, right? So we'll have probably we'll do a U8 pointer, so we can actually just advance it without doing a cast, right? So we'll do like a U8 start, end, and then we'll do like a cursor, right? 3 pointers is all you need. So this is our allocator, and what we're going to do is say, right, void core linear allocator initialize, throw that guy in. Then we're going to say, you know, we could have a deinitialize, but well, yeah, okay, let's have a deinitialize. I probably wouldn't use it for a while, but there we go, let's put it in. So we want to have we want a way to allocate, right? So I have an alloc. So this will take in a U pointer of size, U pointer of alignment, right? Yeah. It's not going to have a way to deallocate, right? But it's going to have a way to deallocate a lot of things. So we want to have a way to sort of like get the cursor. So we'll have a U8 star. We can get the cursor, even though it's a public thing, right? And you can just grab it. This is officially saying you can do that, right? And then we also want a way to sort of like set the cursor. Okay. And voila. This is the API. So it's very easy to implement this type of allocator. Is this going to be thread safe or threads not in the picture right now? So they're kind of not in the picture right now, but how I imagine it is we will just have one allocator per thread, right? But yeah, in the future, I guess there could be two ways, right? We could do it with atomics, or we could just have one per thread and just have different regions of memory for each thread, right? I think that's the way I'll probably go. Like have it local to the subsystem, you know? So let's go and implement these guys. So source core C. Right. So we should be able to use the OS from here. Have we got the OS in here? We haven't. Let's do that. Core, oh no, os.h. So we're going to be using the virtual memory. Well, should we use the virtual memory system or shall we use What should we do? Should we use the virtual memory inside? Yeah, I think we'll use it inside, but ideally we should have a way to pass it in manually. Okay, so we use OS virtual memory, reserve and commit. So reserve and commit is this. What protection are we going to have? Well, we're just going to do read write. Read write protection, please. And the address is going to come out here. ADDR. ADDR. Now, it returns some OS error. So, how are we going to handle errors in this project, right, when it comes to out of memory? Because I guess we're going to have out of memory here, but also out of memory here. So, because it's a game, and the whole idea of this game is to try and pre-allocate things as much as possible. Or if we are going to dynamically allocate, pre-allocate things as much as possible to some maximum size, even if it is dynamically, at runtime. But we don't want to grow an array. We want to say once you've allocated that, that's it. You can obviously deallocate it and then allocate it again if you wanted to, but and do a manual copy. But we don't want to make it easy for you to do that. So I think what we need to do. So I think the best sort of result for this project right now is because if I keep returning a boolean up everywhere and be like, oh, this thing failed, the code starts to get really crazy. You keep returning stuff up the stack, and that can get quite annoying to handle. And you might not want to handle it, and you'll just be doing probably ever, to be honest. So I think what we want to do, and we can always change this, right? But I think what we want to do is we want to probably have an out of memory handler. So how I imagine is if we get out of memory in this game, we'll call the handler, and it will save the game, report the problem, report the call stack to disk, and tell the user out of memory happened. There's a call stack here, right? And then that way it can get fixed, as opposed to, and we'll break in the debugger as well. So I think what we want is a game. We want a game out of memory thing, and it'll go in the main file. So we may need arena boundaries in that case. I'm not sure what you mean by arena boundaries, but yeah, we have a start and an end. So the allocation will happen in initialize itself. In initialize itself. I don't know, I'm not going to have a reallocate at all. The idea is to avoid the reallocate entirely, right? We don't want to reallocate memory because it's just a waste. You have to copy it, and it just promotes really bad design. Hey there, Danzy, how you doing? Oi, oi, oi. How's things been? Been a while. I know I saw your last stream, but yeah, how's things been? But yeah, I had tons of people in last stream, so it's difficult to see. I don't know what to do about the OS result. Should I have multiple success messages? Hmm. No, I'll just say, right, if result is not equal to OS result success. That's what we'll do. So we'll call the game out of memory handler. So we'll probably just declare this here, because we'll create a proper thing in a bit. So this is going to go inside main. So this will have access to the whole system. So be able to shut everything down in here properly. Like it can be like, oh, save this file out, or you know. So ideally, what we want to be able to do is put, while we're deving, right? We want to so if we're debugging, should I have an assertion for, it says debug assertions, but maybe we want like, yeah, same thing. So we'll say if we have the debug assertions on, what we're going to do is we're going to do core breakpoint. So this will put a breakpoint in, and it will just open it right up in the debugger for us, and we can just see it all. So the other thing as well is like when stuff typically aborts, it will give a stack trace out anyway. So maybe I could just abort, you know, and it will just yeah, we could do something way better. You know, maybe we could pass in how much we tried to allocate. But then again, we will just look up the stack and see anyway. So I guess it's not that much of a big deal. Yeah, let's just do that for now. So we've got this handler that we'll just call. This is going to be no return, right? If not defined. Let's just define it, right? Cool. So when that handlers have no return, to say that it will never return. So you put it in places and the compiler won't complain. Well, it's been too hot for me. How's the married life? Yeah, I know you mean. It's oh, last night was hard for me to sleep. But yeah, it's all good. It's really good. Yeah, the wife is on her last week, so literally tomorrow's her last day at work. So she'll be able to like just relax and just wait for the baby, basically. So the baby's due in 1 month. It could come earlier, it could come later. But yeah. Does she like Rust? I don't know. Yeah, I got a baby in the way. I mean, if you're working with threads in the picture, you need a start arena, end arena. Yeah, we've got that, right? We've got the arena. Look, we got start and an end, right? This, right? So allocator start equals ADDR, end equal ADDR plus size, right? Wait a minute, we need to cast this to a, damn it, core pointer, putter, add. Okay. And the cursor just starts where the address is, right? Bam. There you go. So that right there is how we initialize the allocator. How we deinitialize it? Well, we want to like oh, such a sore throat. Yeah, I got a baby in the way. 1 month. Release. So we release some memory back to the operating system. So this one fails. So I don't think this one can fail. So when I say like, you know, failed to release memory, so this should only happen because this should never happen, right? So I want to put another core debug assert, I guess, to say that it's not been initialized. Maybe. No, that doesn't matter. So we're releasing, right? So the size is going to be. Wait, what is? Okay, the reserved address says allocator start, and then the then it will be allocator end takeaway allocator start. Voila. So it might be better for debugging purposes to do this. Size. So we can actually see the value if it were to have a problem, right? Cool. So now how do we write the logic? Remember, we're just incrementing a pointer and making sure it's aligned. So it's pretty simple. Boy, girl, or Velociraptor? Oh. Yeah, it's a boy. So I'm glad it's a boy because, yeah, just to start off with, I think it would probably just be easier to have something like, or just have a boy really, but I would like it my second was a girl though. Hey, not at all. So, right, we want to get the next pointer. Oh, we didn't return a pointer. Oh, that's bad. So this would be like, we kind of want to get the pointer that they will be using, right? So this is the pointer. Allocator pointer. So that's going to be allocator cursor, right? Now we've got to use that lovely align macro that we've got. So the thing is, we should probably do an assertion. Power of 2. Align should be a power of 2. Because if it isn't, then by round up align, int round up align isn't going to work because it's a special trick. We're to do with the way you know, it's doing some special magic to align this power of 2 or this integer to the nearest alignment, right? So say if it's got an alignment of 8 bytes, it rounds it to the nearest multiple of 8. But there's a special trick you can do if the multiple is a power of 2, right? Because the way integers work. So we want to make sure that we take the cursor and round it to the nearest align. Or the shoot. Oh, that's int, that's why, don't mind me. Being silly. So that's the integer one, but we've got a pointer one. Cool. So now we've got a pointer. This is the one we're actually going to return. Okay, so we will return that. But before, we've got to do some checks, right? So now we're going to say, hey, so we've got to work out, like, where's the new cursor? And is the new cursor, so the new cursor is going to be allocator pointer plus size. Now, if the new cursor is greater than, right, the allocator end, so if it goes past the end of the, if this gets pushed past the end of the allocated buffer, then we obviously can't fit this allocation and return that block of memory back. So if that's the case, out of memory, and voila. So we can assume, which is really nice, is this allocate function will never return null, which makes the usage code really simple. The final thing to do is actually update the allocator, and we want to make sure that the cursor is now equal to the new cursor. And that is it. Check firepower 2 for aligned or not. Yeah, exactly. That's all this guy does here. So we just have a pre-made assertion. So we just, well, this is power of 2. This little trick here. And then we run it through this and just, you know, makes it a super nice error. Yeah, I have to learn that down, Z. Yeah, I'm sure it's going to be challenging, but also fun and rewarding. I get a whole month off work, which is really nice. So I get time to adjust and see what this baby is like and capable of. But yeah. And the final thing is set cursor. So this be allocator equal cursor. Voila. So we probably want to assert, right? Since they're allowed to do this, we want to assert and say, right, cursor must be greater than the start, greater than or equal to the start, and it must be, less than the end. So we just want to say, you know, hey, the cursor is out of bounds, right? New cursor P is outside of the linear allocator memory. P dot 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 P. So cursor, allocator start, allocator end. Bam. Cool. So that is a linear allocator done. Amazing. Should the new cursor be aligned according to the power of 2? So you don't have to worry about that. So typically the size, yeah, so whatever they give us as the size, like ideally this size should be a multiple of a line. Is that right? No, it doesn't have to be. It doesn't have to be. But yeah, when you increment the size and you get the new cursor, like the next time you use cursor is you're rounding it up and aligning it anyway, right? So to whatever the next requested alignment is. So for instance, if you have an alignment of 1 on the first allocation, it will be pushed. It will just be some random byte address. It won't be aligned to anything really. So it's aligned to 1 to 1. What is what's the way of saying it? Yeah, so be aligned to 1. So when you do your next allocation, if the next requested alignment is 1, you've not wasted any memory, right? Because if you were to align it to like 16 or something automatically every time, you'll be wasting like 15 bytes at most, right? So yeah, typically you just do it this way. Should be good enough. Awesome. So that's our super quick allocator, and it should be usable. But so we need a thing to start using this in. Now, before we are going to move on to our own custom array type. But what we want to do is probably talk about how we're going to use this allocator, because the problem is if what's the way of saying it? Shoot. Hey there, Lind. Is it possible to create an MMORPG? Well, extremely unlikely. It's quite difficult. It depends on how you're making it, right? And also depends. It highly depends on so many factors. But for the most part, no. Like it sounds like you're just getting into game dev, right? So are you looking into making games and just getting into making games? Is that where you're at? So what we want to be doing is making our own array, but we want to wait for the array to take in a custom allocator. But we're going to possibly have multiple allocators, right? So two ways we can solve this problem. We can either pre-allocate the memory, right, outside, and then free it when we're done manually. But then it's quite verbose. So what we probably want to do is have a way for it to hold a very general allocator. So for that, we're going to have what's known as an allocator interface. Just so we can pass in one type to anything that wants to allocate, and it can just get going. So we're going to fill in this interface. We'll try and keep it very small. So what I want to do is probably have an I allocator, right? So all this is going to do is hold a data pointer, or like the allocator. We'll call it maybe we'll call it instance, right? It points to the instance, the allocator instance. And then we want to have some function pointer, right? So you get hold on to everything. Some function pointer. So that'll take in the allocator instance. Then you want to have the size and the alignment. Right like that. So I've got two ways I can do this, right? I can either have like a vtable, or pass 3 pointers around. because I'm not going to have a realloc. Right, so because I'm not going to have a realloc, let's pass in a pointer. And that can be null. That's it. So what we want to say is like, if pointer equal null, equal null, then it is an allocation. Otherwise, it is a deallocation, right? So this way, it means we can avoid having a v-table, right? So a v-table will mean there'll be an extra jump, an extra pointer dereference, and instead we can just call into a single instead we just call a single function and just do an if statement and just check whether it's an allocation or a deallocation. Just do that there and then. There'll be no reallocation because I don't reallocate in this game, right? Because they just cause bad design, basically, reallocation. So we want to call this like we'll just call NFN, right? We'll pass in the so I think we will just do this, right? If allocated pointer, right? If we have something, return null. I was about to write a null pointer there. Too much C++. So we're just going to say like deallocation, do nothing. Nice. So now we've got this one lovely function. We can have a super lovely macro. What the super lovely macro is going to be doing is say core linear allocator. Allocator linear. I don't know. We want a way to turn it into the allocator thing. Maybe we'll do that. So we pass in the instance, right? Pointer. And we're simply going to return casted version of this to be a dot instance equal instance pointer. And then we'll say dot fn equal this guy here. So now we have a general thing that any function can use to allocate some memory with any allocator. And it doesn't have to know which one it is exactly, which type it is exactly. So, right. Switch case is better than a v-table. It technically generates some macro assembly for both cases, depends on which. Yeah, I didn't realize it is better than a v-table because part of me was thinking that a v-table, or, you know, you're still loading different memory. You know, what's what I saying now? Yeah, this is better because you're going to be coming into this function anyway and loading this into cache anyway to do the allocation, right? That's the way that I think about it. But if this wasn't going to be inlined and it was going to be in a separate function somewhere, I would think it might be the same as a v-table, but I don't have any. I don't know much about that. Do you know much about that, Rohan? Oh yeah, v-table trick interview questions. Yeah, they do that all the time, isn't it? Yeah, the answer is like just don't use v-tables. Hey there, Dr. Maruk. How you doing? How you been? So yeah. Now we're going to move on to our own stack. So what is a stack? right? Why do I call this thing a stack? What is it? It's a dynamic array. That's all it is. So you can think of this thing as like stood vector, right? Or you know, some dynamic array. Now, but it's not stood vector. I'm not just creating another stood vector. And you know, always want to emphasize that I think every project should make their own. Well, they call probably something like a collection class, because you probably want to design it specific for your problem. And you know, every time I look at some language, like literally any language, I can pull out just a handful of problems with the way they've done their arrays and stuff, because they're trying to apply it to every single problem. Whereas if you design something specific for your application, you don't have to deal with the very general class that they have made. So a prime example of this already is we don't return null. We have an out of memory handler. Whereas if you use stood vector, it can return null. What's another thing? So another thing is our stack is going to our global array is it's not going to resize, it's not going to realloc, meaning you don't have to worry about having to reserve a capacity up front. You just make sure that you design your problems around pre-allocating the maximum size, and that's the limitation you design around, as opposed to getting it spontaneously resize, and then you got to track those problems down. You pass into behavioral interview. Awesome. Cheers. What other things? You know, I think if you look at like these newer aged programming languages like Zig, and I think Odin as well, and also Jai. Let's just talk about how this thing looks, right? On their end, right? I'm pretty sure they're all the same from what I remember looking. So you have your data pointer. Obviously, this is going to be typed in some way, but imagine it's typed. Well, let's put T there, right? Anyway, you know, have a count, have a capacity. So this is like what we're going to be doing, right? But if you look into those newer aged program languages like Zig, Odin, Jai, and all of this, they stick in this custom allocator, right? They stick that in there, meaning this thing is now no longer 8, 16, 24 bytes. It's now, you know, even more. It's now 32, maybe even more, right? Well, yeah, it's now 40 bytes. And I think some of them go even higher. And, you know, maybe you want to have stuff next to this, and the more you add that's unnecessary, the more you're making stuff go outside of caches. And if you're using these a lot, you probably don't want to push too much stuff out of caches. So why won't we have, like, why is the allocator there in those languages, and why don't we need one? So the reason why it's there in those languages is probably because it resizes, like when you push stuff on your array, or your stack in this case, you know, you append stuff to it, and then it could end up reallocating. It might have to call into this, right? Use the allocator, right? And then allocate some more. Wait, we can do some drawings. You might have your slab of memory, right? And you've pushed elements on, and you're about to push one more element on, and turns out you've run out of space. So what you need to do is you need to actually allocate a new slab of memory, which is twice the size, right? Did that work? Yes. And then you copy this to here, right? And then you get a new pointer, right? There's many problems with this. One, you've actually got to like call a custom allocator, call a custom allocator, copy memory. Depending on the size, it could be a big big thing you're copying. But also the pointers move. So if you have a pointer which goes into this piece of memory, I mean, you do this reallocation. Well, now this thing gets deallocated, and now you're pointing into memory that is potentially given to another thing, and you will overwrite it, or it's given back to the operating system and it will crash your program. So you don't have to go around and patch the pointers, or you don't have to go around and patch the pointers if you don't do something like this. But also, when is this allocator going to be used now? Well, it's only going to be used when we create or when we deinitialize the stack. We're gonna know, like, which means we can just store this. Like, imagine if you have tons of these stack things, right? A, B, C, D, E. And imagine if these all use the same allocator. Well, what you've gone and done is you've just put this, and then maybe you store the allocator here as well outside because you need to store it outside. And you're going to repeat this in all of these things. And it's like, so you could have just, so given our constraints, we can just pass it in when we initialize and when we deinitialize. So we don't need it in here, right? And this is why I say, like, an application should design it to their problem. Yeah, that's good. Hey there, Tony. Welcome. Yeah. So, oh shoot. Close the chat on my phone. No. All right, it's coming back. Yeah. So basically, just don't design it in a very poor way, and then you can cut those things out. So, design it specific for your problem. So the next issue is, okay, so you could have also solved the problem by passing in the allocator every single time you push on an element, but then it just makes the API really crazy. So yeah, that's another way of solving it. Okay. So let's go ahead and make this thing. So how are we going to do this T-type here in C, right? How are we going to do this T-type in C? So ideally, I do want to have it laid out like this. There is a trick you can do, which is like, so if you go over to like, so originally like Sean Barrett came up with this thing called like stretchy buffer. So he makes like STP image and true type, STP true type, right? So here's a very minimal version of what goes on. So basically, like, where's the header type? Oh, okay, there is. It's easier just to explain what this is. So what Sean Barrett came up with, and it's quite interesting, but I think we don't want to go this route, even though it will create a bit of an annoyance for us. But it means it'll be more type safe. So basically, like what Sean Barrett came up with is you can allocate a region of, like when you make your array, you allocate what you need plus a little extra header, right? And in this header goes the count and the capacity, and anything else you want to chuck in here. If you want to chuck in an allocator, you can chuck it in there. So, but what you do is you hold the pointer to type T here. So you basically, maybe you have an array of int. You allocate enough room for this plus the header beforehand, and so you'll allocate this pointer. You'll set this up here, and then you'll add the header and you return this one. Make sure it's all aligned and everything. But the problem with this approach is that yes, you'll have a bunch of, if you were like your stack or your array is now just a pointer size, and you might be saying this is even better than your one because yours is 24 bytes, right? But the problem is every time you want to push something on, you could be all the way up here. It could be a really big really big stack or whatever, when you want to push something on, and maybe this is like, you know, tons of megs or whatever in between the start and here, you have to read the count in here, check it's less than the capacity, and then increment it, and then you can use the previous count to sort of add the next element on, right? But the problem with that is the fact that you have to load this in you have to load this in your cache. Whereas when you access this pointer here, if you had the size information right next to it, ideally the count and the capacity would be in cache, right? Because it's just next door. So that's the downside with this approach, and it's not type safe because you can't know the difference between integer pointer and just a regular integer pointer, or just maybe there's a hash table that's implemented the same way or something, right? It's not that type safe, but it's a really cool idea. I've done stuff like this in the past, but I want to do something different for this project. I'll stretch your buffer. Hey there, Perry. How you doing? How's it going? How's my favorite mod? How's he doing? Oh, Mel. Void Star for the win. Yes, you could use Void Star, but the problem with Void Star is you won't have distinct types between your stacks. So we could go and do a Void Star here. I don't know why I had that much padding, but we could have Void Star here. Oh no, because I had the custom allocator there, didn't I? Right. But then the problem is when you have your stack of A and B and C and D. Thank you so much for the sub. Appreciate it. Welcome, welcome. Thank you there, Rohan. Appreciate it. Welcome to the club. Good, thanks, mate. How's your mama be? Yeah, doing good. I'm a little bit ill. I drank too many of these over the weekend. I drank like 5 or 6 on Saturday and Sunday separately. So, you know, got that caffeine feeling in my face. Other than that, doing really good. We're doing excellent. My wife's got her last day off work, and then we got 1 month until the baby comes. So hopefully it comes a bit earlier. But yeah, other than that, all good. Yeah, obviously when the baby comes, I don't know what will happen with streams. I might take a week off, maybe a little bit longer. I'm not sure yet. We'll just see as it comes. But yeah, doing great. Yeah. So the problem is maybe this is a stack of int and this is a stack of float, right, or whatever, and you cannot distinctly tell the difference between these types. So it kind of sucks, right? So what we're going to do is we're going to have the core stack like that. And this is our void core stack, right? Okay. Now this is where the fun begins. Anakin Skywalker. So what we're going to do is we're going to do a core define. Core define stack T. And we're going to define our own stack type. So do the paste up. It's called token pasting. I didn't make it up, it's concatenation. But there you go. And voila. So what we're going to have is a custom type be declared. So every single time we manually so do a core stack T like this, and that'll just be something like this. And we missed something. Void is now T. Okay. So this is how we're going to deal with dynamic. This is how we're going to do with like creating a type safe stack for our type. But the only problem with this, okay, 2 seconds. Yeah, so the only problem with this is every single time we make a structure or anything, we have to do core define as an example, U pointer. So core define stack. We have to manually declare each type of stack that we want to use. Is there any problem with this approach? Other than that, it's pretty great. But there might be some problems when we make our functions for this, but we'll see. But so basically we declare like a custom structure of something, right? We're gonna have to make sure that we make a stack of something, right? And that's all we have to do. And then we can start using stack of something. And that's it. So that will give us type safety. Now, one thing that we do want to make sure that we can do as well is also forward declare this. So we also want a way to say declare stack, and that's just going to do this. So that maybe we have a pointer to a stack of t, right? So we have a pointer to a stack of integers. We can then forward declare it, but not have to declare the, wait, is that right? Yeah, but not have to. Yeah, this will probably be super rare, but it might happen. So we'll just do it just in case. Sweet. Let's make sure I got my declares and defines in the right way. Always confusing because they both begin with D. So C, define, verse, declare. So the way that I think about it, so I could be wrong. Declare is like forward declaration, right? Whereas define is like I've defined the implementation of this, right? That's the way I try to remember it. So hopefully that's right. Declaration means the variable has only been declared and its memory is allocated, but no value is set. However, definition means the variables have been initialized. That's not quite what I want. Declaration, basic attributes. Yep, and the definition provides all the details. Yep, so we are right. We're right in that regard. Good. Very good. Right. Hey, Under Closure, how you doing? Good to see you. When baby comes, he says she streams while you take a nap. Yes. Maybe that'd be really poor. But yeah. Or maybe have like a baby stream, you know, just like put baby here, get jamming, you know. That'd be really bad. But yeah. Yeah, just sort of have the food at the side. Yeah. I'm good. A little bit ill, but other than that, we're doing really good. Drunk too many caffeines, you know. But you need to check regarding T-type. Do I? We'll see. Oh, I've done this before. It can be a bit annoying. You want to stack up pointers from that, if I can remember. Yes. That's interesting. So yeah, you have to type def it. So yeah, that's a good point. Thank you for bringing that up. So if you want to say define stack of int pointer, right? You basically, like this doesn't work, right? Because you're saying stringify a star, and that's not a valid identifier thing, right? So what you need to actually do is say type def int star int putter, right? And use all those int putters, and that'll work, right? Sorry, there we go, that'll work. So yeah, or you can wrap in a structure. I'll say this way. Awesome. Right. So now, how are we going to write functions for this thing? We have a generic type that gets declared. How are we going to write functions for this? So we have this guy, our void friend. So what we're going to do is so again, return void when you create. So core stack initialize. Pass in so we have a initialize underscore. So this is our typeless version. Maybe we could say void at the end, right? Maybe, yeah, we'll do that. So you pass in your stack, You'll point it to your stack, yep. And then you say, so when you initialize, how are we going to initialize? Well, we want to have some form of initial capacity. And we obviously want to have a custom allocator that comes in, right? So it's core iAllocator. So we have our allocator interface, and then we can custom allocate whatever we want. So that's awesome. And we never fail, because if we do fail, we handler, right? Out of memory handler. Bam. Then when we deallocate, take in the allocator and deallocate the stack. So now we don't have to store an allocator because this stack will never resize. So let's get these guys in. So right, so this isn't quite done yet. I could type more out, but before I do that, let's make sure we finish exactly what we need. So we then use a macro to define the non-void version. You then pass in the stuff you need. Now we're actually missing an argument. We need to know the element size and the element align. So we could go ahead and just assume that and align everything to 16 bytes, but then you're just wasting space. And then what happens if you need to use AVX512, which requires 32 byte alignment? We have to up that number and have some max align. So we'll just pass it in, set it up. The compiler might inline this, or it might not. If it doesn't inline it, it's kind of nice because we get some code that is shared, and that will probably stay in the cache, right? But if it does inline it, it means a lot of these things which are constants, just become constants. But we'll see. We'll see. Anyway. So what we're going to do is cast our stack. So there is a bit of unsafety here. We are going to cast whatever this type is into this, right? So that's a problem, right? So what we might do is we could indeed, but like, so this means that any type that, so is there a way to get around this? Well, we could do union. Is there a way to do union? Maybe we can do a union. This would be super hacky. So if we did a union, yeah, this is the way you do it. Get ready for it. I could call it typeless, but I've used the word void now. Void stack, something like that, right? And then we just do stack. So this is the way you can get around it, and then it's kind of, oh no, it is type safe, right? 100% type safe. So you can just say return the address. So it's going to offset it by nothing because it's a union, and it will, yeah, it's completely type safe. So that's a really neat trick we can do. By the way, Intel 13 Gen doesn't have AVX512, so better use EXE for time being. Yeah, huh. But didn't they... Wait, what is the Intel Gen they're on? What are they on now? 13. Oh, did they remove it? I keep hearing conflicting stuff on this from people. It's really silly. So what happened is someone was telling me AVX512 is basically ready now because they fixed all the problems. Like... So they disabled it apparently in Alder Lake. Yeah, I don't know which one that is. Yeah, it's a weird story because you got people, you got ARM and your GPUs which have like massive vector, I guess it's kind of different though, isn't it? They're not registers in GPUs, but yeah, they're all very wide registers. So the allocator goes in, and then we pass in size of. Now here's the next trick. Size of t. Oh no, I've just found a problem. So we either have to pass in t at the start here, because, right, in C, it's really awesome, but there's a sad side to the story. You can do size of expression. So you can have an expression and it gets you the size of a type. So you can do dereference this and it gets the size of whatever t is. Amazing. But even though it's basically the same, like, old C compilers wouldn't do this, but in new C compilers, they could totally do this. Like in my C compiler, I have support for it, but they just didn't put it in the standard, which is bloody annoying. You cannot do a line of expression. You just can't do it. It's an extension. Really annoying. So we can do it technically because every platform that we're going to support, we're going to use Clang on every platform. So technically we can do it. But it is an extension. So what we could do is do a line of, and then if it fails, just return maximum alignment. So we can do a custom align of. It's really bad. So C align of expression. They didn't even add it in C23, I don't think. It's really annoying. See, it's always type ID. Well, that's C++. Type name. The worst. So I can either pass in T manually, or because it's a stack, we just max align it, or we do a very special thing. So the thing is about, we've got pedantic mode on. Pedantic means we want to be C compliant, but we could. So in GNU C. Oh wait, we have type of in C23. And type of is is in GNU C as well. Right, so maybe we can do. So the thing is about type of is we're not gonna. Like, so every compiler. We might have to turn off pedantic though, But we can maybe disable the warning. Let's try it out. So we might say define core type of T, and this will be type of. So if def GNU C, then it's C23 we get access to it. So maybe, yeah, that's the way we're rolling. So we have underscore type of in GNU C. And then we'll just do an error. Else error. Type of is unsupported on this platform. Or we could say has not been implemented, right? To do, so is there an if def for C23? No, not 32, 23. Because they forgot to put it in the final spec, the macro for it. They forgot to put the macro in it. Check if compiler is C23. Yeah, so it's hard to guess because you have to know the exact year and month it was made. And I forgot. This is what we want. Because they forgot to implement this in the final spec, I think. This is it. Okay, good. So apparently we can say if def right, if defined, no, if standard C version is greater than or equal to, oh come on, is greater than or equal to C23, define that as type of, and then we can say else lf defined, like that. Nice. So we can roll with that now, and that'll be legal in C at some point, but in the old C compilers we can still use it because we're going to be basically using Clang anyway, right? Across every platform. So, although I do want to stick to C standard where possible, that should hopefully be fine. That gets around having to include have T here, right? T right there. That'll be really annoying. So that's really awesome, and we can implement that soon. But let's get this. So we need the size in line to come in as well here when we do a deinitialize. Okay. So there's the deinitialize. So that's great. We don't want to pass in the capacity. Let's get rid of that. Cool. So what is the next thing we need to do? So we like to be able to push on stacks. We like being able to push and pop, right? So push on the end, pop off the end, insert, resize, but not reallocate, right? So let's do resize first. So no allocator anymore. So count, what's the new count? When I was doing this, I ended up using define before all my procedures where one of the arguments was a type. Ooh. I ended up using define before all my procedures where one argument was the type. I see. So so when you defined your stack, you pre-made all the inline functions for it. I see. Yeah, that's an interesting way you can do it. Yeah, that's another way you can do it. Yeah, I think I've done that in the past. But yeah, then it's more code that gets created. But yeah, that's a way around this. That's for sure. Doing that. That's a good idea. So we want a new count. Good. Resize. new count, size align, bam. Right, good. Next one. So the next thing to do is we want to push. So we're going to start off with a push many, right? And then push will just come off of push many. So the idea is it returns a pointer. Now this pointer is never null, right? So which is really great to assume. So we can say, how much are we pushing on? What's the amount that we're pushing on? Push many. Then we're going to say amount. So, you know, people might be like, oh, I'm going to pass in a pointer when I do this, right? I'm going to pass in a pointer for the stuff I'm pushing on. But then the problem with that is you have to put it in some array somewhere else and push it on. It's really annoying. So it's just better if you manually get it back and you can mem copy it, and then it doesn't go in the function itself. But then this function is very simple. It just extends the stack, gives you back a pointer, off you go. Essentially, it's like the allocator we've just made, right? It's a linear allocator in a way. So this is pretty decent. So there's amount. Cool. So we're going to make a couple more macro things. We're going to be having push many push. So push does nothing, and it just calls push many with an amount of 1, and then just, yeah, so it's a nice shorthand, very nice. Now we also want a pop many, and this can give you back, yeah, I think it would just serve you pop too many. Yeah, exactly, it worked well enough, but none of the stacks are types either. Right, I see. Yeah, the problem is you have to explicitly declare it, but other than that, like, it works really well for this project, right? But if you start having like a project where it's sort of got all these little shared libraries everywhere, you definitely have to be careful where you, like, the library might not declare the stack type, but you want to use it as a stack. So you declare it in your library that uses that library, but then and you put it in your public interface because you need it there, and then another library ends up needing to do the same. And yeah, so you have to make sure you put it all in the right place, basically. You do it this way. Yeah, pop many is pretty decent. Oh, I forgot to do type of. So we're gonna do a super lovely cast. So we're gonna cast it into type of like that. So this way, what it means is that we get it to be casted into a very, an actual type, meaning it'll be an error if you assign the void pointer or the types pointer to something other than void. So that'll be really nice. Cool. So there's many more functions we want to add because this is only scratching the surface. We also want to have the ability, even though it's not great, now there's two different types of remove, because you kind of want to remove from the center of an array, or a stack in this case, sometimes. So there's two different variants of this, and I like to make them explicitly named. So we're going to say remove shift, right? So we look for pop. So remove shift many, remove shift. So this one's the slow version. This one's potentially slow. If you have a very large array, imagine you have a very, very large stack, right? Tons of elements, and you remove this element here, right? You've got a mem copy. All of these elements that come after over this element. So you got to shift them all to the left by 1. And if that's megabytes big, it's megabytes worth of copying. Now there's another way you can remove, and this is so there's remove shift, as I like to call it, and then remove swap. So a swap remove is another thing you can do. Remove, oh my days, what did I just do? So shift, remove, swap. So this one's the fast one. So what this one does is, say if you want to remove this element here, what you can do is you can just take the element at the end, right? And you copy it over that element, and then you shrink the size of your array so it becomes one less. Now this is great if you don't care about the order, but if you care about the order, it's not good. So there's that. So this is an optimization that you can use. But yeah, we want to be explicit about how you remove, because it is very sensitive on that one. So yeah, that is good. So is that everything we basically need? So, you know, if you take a look at any other like implementation of a growing array or anything, they have tons and tons of they have absolutely tons and tons of functions, and they take all types of arguments, but we've tried to minimize them down to something very oh, we're missing an index here. Try to minimize that, you know. So we need an index. Missed that one. Hey, what happened to my chat got disconnected. Is the stream going fine? Yeah, stream's going fine. Okay. Have another drink. Index, 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 index. Oh, right. That's good. So with the ability to we need insert. That's the other one we missed. Right, let's get the one in there. So other than remove, you also want to have the ability to insert. So if you insert, you've got to shift everything. But you could technically do a swap insert. But then if you're doing a swap insert, it's not really... Like, I don't see the point of a swap insert, because if you're doing an insert, you want it to be in a specific order, and it's a very specific thing you're doing, right? So I think you will implement that manually. So we'll just do a insert. You know, I'm gonna look at my old implementations and see if I did that. Can I look at that? I've got these laying about in a very easy place. So what else did I do? So this is one where I did the... This one isn't as good, I don't like it as much. Yeah, I just did a regular insert. Right, get, I need a get function maybe. Yeah, let's do a bounds check. That's a good point. We need bounds checking. I'm pushing strings on. Right, those are the other ones we need. Pushing strings and these special bounds checks. Yes. Right, so let's get these in, and then we'll go and implement this all. Be very quick, we can do this. So, oh, we don't have a custom string type. So, yeah, we're probably going to need this. Yeah, let's just throw a custom string type in as well. Yeah, this would be interesting. Let's get one of these in. We'll put it above the stack. Right, we'll implement that in a minute. Let's just finish this stack and then just tick it all off. So I have like a core string. And then we want to replace like, yeah. Excellent. Right. So we're going to have, these are types, right, to the specific string. Type, right. Prefer kdevelop over type. If I'm not using NeoVim. Yeah, but kdevelop feels like a whole IDE, right? But yeah, I want, yeah, this is, you know, maybe, yeah, I don't use it because it's just default on the system, you know. It's like the notepad in a way. But, you know, it's obviously much better than notepad. The syntax highlighting is horrible though. Not a fan of that. But yeah, how is kdevelop? Is it like a full-on IDE? Right, so what is our string type? Do I want to do C string type? Probably best. So the thing is about string, yeah, we probably want to make them C string compatible, these strings, but it's just a sized string. It comes with a size, so you don't have to, yes, it's cached. So I think that's good. So we want to define like all of our core types. So let's get those in. Define core, define stack. So we want like char. Oh my days, sorry. Being a scrub. U8, U16, U32, U64, U pointer. And then we'll just do the signed versions, yeah? All right, got all those in now. So this is also going to be... Oh, did we not define our... Oh, yeah. I don't know. I typically like macros to all be uppercase, but since it's like a type thing, we'll do it like that. It's a... Yeah. VA list. Ugh. You have to include standard or whatever for that. Can we afford declare VA list? Maybe we can get away with that. Because the problem is if you include the header, then it's included everywhere because it's in core. And that's really not good. But I also want this as well. I want a sort of a printf format attribute. So define core printf attribute. So I have like start, end. Something like that. Core printf. So it was 2.3, wasn't it? Yeah. Two, three. Start end. So in Clang and GCC, this would give us errors. It's really good. I don't think it's available in MSVC. But yeah, so it gives you proper printf errors on a custom formatting thing, which is super nice. Just drop that there. So VA list. You kind of need VA arg, but if I look at that header, standard arg, that's what I meant. Right, built in, it's a type def, but then it might not be that on all platforms. So maybe we can see on Linux. This is good, but maybe it's not. You know, it's not a lot of include, which is super nice. But on some other platforms, it might not be. All right. All right. So we finished our stack now. This is... Oh, no, we haven't finished it. Give me a sec. One more thing. One more thing. We want our bounds checked get. Right? Because in C, indexing into arrays is basically unsafe, and we want a runtime check in debug mode. But in release mode, we want to get rid of that runtime check. So we want to provide super lovely things. Oh, I'm missing stack count as well. Oh, no, we don't need stack count. That's good. Hey there, Don. How you doing? I have a riddle. What comes before Friday but after Wednesday? Thursday? I hope I can get it. I'm super brain dead. Maybe. Hey, Mr. Shelby. How you doing? It's been a while. How are you two doing? You been up to much? So we want to have our sort of a debug assertion. You know, maybe we could just debug array bounds check this thing. This is called like debug assert array bounds, but I cannot see for the life of me a debug assert, right? Plonker. What is this? So you could probably compile that if it did a debug assert, because that will compile that to nothing. I don't know if it can. So the reason why I want to do it like that is so we can get a return type. A return. But if we made debug assert return an integer, you could probably question mark it. That'd be interesting. But it's called no return. But I think I made it return. I didn't. Come on, you pointer. Right. So the beauty about that. This is the beauty about it. Now with any. So I think what we want to do is say. Wait a minute. Is it this one? Yeah. So you want to say condition question mark 1. And the other one will never return, right? So then this means you'll get back when you do a debug assert. So you debug assert that is less than that. Then, if not, you do this super lovely error message. All of the code. Now, you do a question mark at the end, and then you say, so if that succeeded, which it will always succeed or no return fail, right? Give me index. If not, give me oh, wait a minute. Is that true? Am I thinking about that wrong? Maybe I'm thinking about this wrong. Nice. Dinner Project and Joy. Cool. How are you finding it? I've heard decent things about Joy. Like how people can get started in it quite easily. But yeah. Right, I'm going to switch on the lights because it's getting quite dark in here. Oh, my head. Oh, so ill. Right, the green screen is bugged. Oh, it's this way. Yeah. Ta-da. I could have just moved my screen. I just did the complete plonker thing. Ta-da! Ah! Do 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 do. Damn it, green screens. Where's the filter thing? This thing. Ah. That'll do. Why not, if not condition failed, question mark? Because I don't think that'll work, Mr. Shelby. I'm trying to do a thing where I can return the index as an expression from here. So yeah, I could do an if statement. No, but I can't do a statement because there's no expressions. So this will get compiled out into this less than that. Right? And then I question mark that in release. You bugger. And what I really want... Hey there, Dazzy. Yeah, I think Perry was asking about whether or not if you knew the baby was on the way. I think that was it. So could I do this debug assert thing? I guess I could just if def it, right? Yeah, I'll just have to if def it. I was trying to do something really clever, right? But I don't know if there's a way to do it because I want the condition to stay around because then you don't get the problem where stuff gets compiled out and you don't realize, right? But I think what we're going to do is like debug array bounds check, just return index, right? Comma operator returns the last thing, right? So we can say void cast void count. Comma index, put that in, and then that will return the index at the end, right? So then I can say in actual debug mode, just do this. Oh my days, did I get that wrong? Yeah. Define this as... Wait. Define this as assert. See, I could have... I want to have one that sticks around, right? I don't know why I have an if not defined core assert. This is my own code base. Get out of there. Whereas this one probably wants, say, assert array bounds. And we have that always. And then it returns that if not 0, right? Yes, so this will just be that basically. Yeah? Excellent, that'll do it. So yeah, so now what this means is we can use this lovely macro as an expression and we don't have to write if defs anymore in other places. So when we do our stack get, we can literally just do this. Index stack count. Yeah. And then it returns the index from that check. And then we can use it there, meaning we don't need this if-def anymore, because in release, it'll just compile out onto an index, right? Awesome. So we also have get first and get last. We also want to get back, right? Where you can index from the back, which is super nice. So that is basically count, take index, take 1. So you can index from the back, which I don't see too much inside, you know, when you have a custom stack, or sorry, when you have a stack type in a language, I don't see this function too much. It is potentially dangerous, but hey, we're programming in C at the end of the day. Cool. So this is complete now. We can go ahead and implement this, which I want to do. But before we do this, let's just sort out this string thing we've just done, and then we'll go and implement this initialize, the initialize, resize, push many, pop many, insert many, shift remove, remove swap, right? And then these push string ones should be super nice. Dun, 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 dun. So let's just implement this core string thing. So why do we have this? So, you know, C strings, they can be great. You know, there are advantages to having C strings where they are null terminated, but I think what we want to offer, so all of our strings will be null terminated, even if it is this thing. But what we want to offer is the ability to cache the size and stick it next to the string pointer and have it in some kind of thing that we can just use, because that way we can primarily use this and then just use the C string where it makes sense, right? So we have ways of creating it like this, like a core string, from, you know, with stringline as well. We can also check for equality and with a literal as well, fair play. String slice, sure, does an inline thing. So the problem is when you do the string slice is it no longer becomes a C string, right? So I guess if you're slicing strings up, you just have to be aware of that. Yeah, that's fine. I think that's fine. Right, and then we also want a way to sort of dynamically allocate strings in a formatted way using a custom allocator. So you can like, so this thing where we do this attribute thing, right? Core printf attribute, right? And I think, oh, come on. Oh, 2, 3. Excellent. So, yeah. This means if we want to create a very short-lived string or maybe a long-lived string, depending on the allocator we use, we can just like fabricate these strings very easily with a nice, easy API that's made up, turn integers into strings or some, basically like printf but into a string. So that'll be nice. But yeah, that'd be awesome. So what we're going to do is we're going to implement these things. We'll come back and do this core string format thing in a minute. Or should we start with that one? I don't know. Yeah. All right. Well, let's get these things, bring it into the core, just implement it all. Be super easy. But yeah, if anyone has any questions about what we've got so far, wants to have a bit of a highlight of what's gone on, just ask and I'll happily drill into that so you understand what we're doing. I'll try and just make comments on why it's designed a certain way as well when we go over and implement it too. All right, so now we're in the C file. We're just going to delete all the stuff that's been kind of declared in the header. So, all right. I could copy and paste this from an implementation I've already done, but it's just more fun if you guys get to see me write from scratch and to show you how easy something like this can be. And you don't have to overcomplicate it either. Yeah. Okay. Cool. Let's go ahead and... Right. So we're going to start off with this string one, right? This is the first time we get to use our custom allocator interface. So we'll give a quick recap for those who weren't here when we made it. So basically we have this linear allocator, right, which just sort of bump allocates. It's the fastest allocator, the most simplest allocator you can have. But we want a way to allow for our code when we create allocations. We want to have a general way where we don't have to create different functions just because we pass in you're using a different allocator to allocate. So this is where the allocator interface comes in. It's just this thing here. And essentially all it's going to do is just it holds the pointer to the instance of the allocator. So you pass in the instance of this allocator here, store a pointer to that, and then we store the actual allocator function here. And if this pointer is passed in null, it's a allocation. If not, it's a deallocation. And we don't have any reallocates because, in my opinion, a reallocate just causes like a lot of problems. So it's just easier if you can just allocate things up front and just know the size of things, and maybe reallocate in some very small areas in the code base, but very explicitly, right? How do I come up with this in such a short period of time? It's because I've done this like so many times. I've made like over 20 custom allocators, custom collection. Like I've implemented them over 20 times. So I have a good idea of like what I like. And I do jump from one design to another design and this design because I just change my mind every time I do it. So but yeah, I just and sometimes I would implement it just to try out a design and see how good it is. But yeah, this is where I'm currently at, and I try and keep a very slim interface. I'm not passing in a lot of things, and I always make assumptions like, oh, this pointer never returns null, so it makes the API a lot better. But yeah, just tons of practice basically, and just get an idea of what I want. Plus, I keep code around and I sort of like copy and paste it in if I agree with that, and so we can get going quicker, like we did with the string thing, right? I forgot about this thing. This is really handy, being able to just build a string really quick. So it's very easy to forget these things, but yeah, just practice. So we want a super lovely function to. We want to like say core alloc, right? Just an alloc thing. So you pass in the I allocator, right? Then you pass in the size and a line. And then all this is going to do is just call ialloc, the function, right? That's here. And then it's this thing. So then that will be ialloc instance, right? And then it will be size and then a line. Wait a minute, we need the null in there, right? Null. Excellent. So then if we do a dealloc, we want to have a pointer. So allocated pointer. So this is our interface, right? That's all it is. And there you go. That right there is how we do allocations, right? Keep it simple. Yeah. Yeah. Yeah, it's just like experience of when I've done it in the past is all. Yeah. Um I've found like after like programming for so long as well, is I've started to settle on, but not fully settle on what sort of like what are the basic principles that I like when I program, like fix allocate things up front. But you can doesn't mean you can't work that size out at runtime. Typically you want to keep the allocations with the operating system at minimum. Um, and then sort of just reassess what it's like for an application that I'm building. Maybe I try something different. But yeah, just that sort of stuff really. Right, so these are going to be super handy. One thing I did forget is to cast this function pointer into this. Because this is a void instance, whereas this one is it's typed. So these are technically different, but it should be fine. Oh, this needs to return a pointer. Right, that would have been crazy. Cool. So now we get to use core alloc, right, in here. So basically what we need to be able to do is allocate, so say core string. And then we'll end up saying like string dot data equal core alloc, right? We need the allocator. Yeah, let's do that. We need the allocator. And then we also need the size and the alignment. So the alignment is just 1 because it's an array of bytes. So all we need to do is say we need a size. So we need to calculate that. And we need some form of, so it would be a line of char. So that'll get us our pointer. Then our string.size will be size. And then we basically need a way to sort of set it up and then ultimately return it. Okay, so let's fill in the blanks. There's 2 blanks. There's a before this and after this. So let's get the size. So one function you can use to just do all this format stuff for you is just snprintf, right? But you can do this, right? snprintf, wait a minute, count or size is equal to snprintf, pass in null and pass in 0. I forgot which one it is, but yeah, you can pass in null or 0. I forgot which one it is exactly, but I just pass in both. When you do this, snprintf switches into a special mode where it just gives you the size of what the formatted string would actually be. So we're going to pass in args copy. Now what is args copy exactly? So we need, because we're going to be calling this twice, right? We'll call it once to measure, second time to populate. When you use VA args, it's basic. I don't know how it works under hood, but it's probably something to do with pointers, and it's like they just jump through. They sort of advance the pointer, right? Something like that. So you lose the state. So what you need to be able to do is make a copy of this. So you can do VA copy. And destination source, the best order. Awesome. And then what we need to be able to do is say, right, VA start. We're going to start args copy. And from format. Oh wait, sorry. No, I got completely confused. This is for the one below. Right. Ignore me. Yeah, I think that's right. We've got to try this out. So you do a copy, you use that. Internally, this will iterate over using VARG. Yep. So that should be fine. Why didn't this work? Maybe we should wrap this in a thing. It's not the problem, but we're going to wrap it anyway. Function call. Ooh, don't do a pointer there. Right, that's the problem. Come on. Expected expression. What are you talking about? Ah, right, I see. By valley, that's what we want. We good? Align. Instance, null, size, align. Do we not have a line of done? Ah, classic. All right, define a line of as a line of. A line as a line as. Cool. Right. So now we call it a set. So we should really assert here. I forgot what it is. The exact thing. So we've got to read the docs. But so if you man those docs, what you'll find is there's a return arg. So there's an encoding error. So negative value is returned. Core assert. Right, probably just debug assert. Core debug assert. Size is greater than or equal to 0. Then that's going to be printf format string is invalid. Right. Awesome. So then that's basically it, how you do it. So the problem is you don't typically call this function. You only call it if you've got a function like this, right, with the variable arguments. So all you need to do is make sure you do a VA start with your VA list args. I always forget this order. AP and param. Right, args format. Right, because what is the thing before the VA args? And then it can do end. And you call this allocator format args. And you get your string, core string, and then return string. Excellent. Very cool. Hey there, Nico, how you doing? Do you need to free the copy? Good question. Hey there, Nadiello. That's a good question. Maybe snprintf does that, right? But let's take a look. Yeah, because that'll do a VA start and VA end. Versions of C23 do not require the second parameter. What? Really? Okay. Clearly solving the real problems. I have no idea what that's useful, to be honest. Let's have a look. Let's man these VA copies. VA. So I think it will just be a pointer, right? You're copying a pointer to the stack. I think VA list will basically be a pointer. I don't think there's any allocation involved. Same behavior as VA start as if there's destination. followed by the same number of VARG invocations. An obvious implementation would be the VLS as a pointer as the stack frame, and the setup is most common. There seems to be nothing against this, but unfortunately it seems also systems make an array of pointers with a length of 1. So, right. Yeah, so it's a pointer on most places, but some do this apparently. So, finally, systems with arguments that are passed in registers. It's necessary for a start to allocate memory. Store the requirements there. Oh, already is an allocate. Ugh. Also, and now end to free it again. To comment the situation, adds the macro VA copy so that the above can be replaced by this. Must be matched with an end. I didn't know that. Thank you. So basically on some platforms that will probably be an issue, right? So I guess in the code I've written so far, I've never done that. So we need to say, oh, maybe I have done it, but I don't remember doing it. So we'll do a nice little thing like that. Then, but to be honest, SNPrintf won't call the end because we do the start and end here. Excellent. Thank you, Nadula. Appreciate it. Hey there, Davros. Welcome. Have you ever tried doing a long jump before calling VA end? Ah, interesting. No, I've never done that personally. I've used a long jump in one project, and that's the compiler, but I don't do it inside these guys. But yeah, that's interesting. I'll be aware of that. All right, so that's our string, like stuff, so we can make these quick strings. So now let's get to implementing this stack, right? So we'll give a quick rundown of like this stack again for those who are not, familiar with what we've done. So we've got like a void version of the stack, right? And then we have to manually define our stack types like so. But we can also forward declare it if we want. It's just a pointer version of it. It's also a union, so we can access the void part of it. And so that means our function calls are type safe down here. We've got some safe ways to get a pointer to an element in the stack in debug builds. So it's like a bounds check, right? But in release builds that will be compiled out. Our stacks are basically a growable array where the stacks are a growable array where the size stays the same, the capacity stays the same, and you cannot reallocate it unless you create a new one, copy it, and then deinitialize the old one. So it has to be explicit resizing if you want to do that. But you can obviously resize the count, that's fine, but you can't resize the capacity. So when you allocate it initially, that's just the allocation you get, which is really great because then it means we don't have to store a custom allocator in here or pass it in every time we push. Instead, we can just pass it in when we start and end. And yeah, so we've got like resize, that resizes the count, and you can have uninitialized memory maybe, but you can grow and shrink it. Push and pop. Also got insert and a couple of removes. One thing to take note is that these... Oh, I missed something there. One thing to take note is that when they return a pointer, okay, when they return a pointer, there we go, that pointer is always valid. So if we get an allocation failure, it will go into the killer and the out of memory handler, and that will kill the program but shut down gracefully. So that's the plan we're going with, because then it makes the usage code really nice, and we can just do some really easy things. Have I tried doing a long jump? Oh no, sorry, read that one. What if the size of your stack is 0 and you're applying get to the last element? So you would do a -1, it will overflow. It will underflow and become all bits on, right? All the bits will be on, be the largest number, and then it will go into the bounds check, and then it will fail. But in release builds, obviously that will probably hit something. Yeah, it will hit something. Right, the thing before you. But yeah, the thing before the stack. But yeah, that's fine. Like that's the point of it being in release and debug builds, right? Is that we have the safety in debug, but not in release build. Okay, so let's allocate these guys. So we want to call. So essentially, we're going to say stack data. So we could do an assertion to say this has already been initialized, right? So 0 is initialization. And I think that is probably a decent idea. So I want to say like is initialized. And that'll just check stack data, right? So we'll just say stack data. Now we probably want to have a assertion. Stack is initialized. So this is just going to wrap. You know, do we ever want this? Yeah, we might want this for some reason. But yeah, let's just do that, right? So we'll just do a nice core debug assert. So we'll do a debug assert. And we'll just say stack is stack is not initialized. Something like that. So for initialize, we actually want to do it manually, right? But the rest of them will get the other one. Has already been initialized. Yeah. Nice. So we'll put this nice assertion on all of these, right? And now we can say core alloc allocator element, wait a minute, capacity times element size and then element align. So that gets us all of our, yeah, so that will get us a nice range of memory for this stack and it will never change. Then we say stack count is equal to 0 and then capacity equal capacity and then that is it, right? We don't default initialize anything. You know, depending on your allocator, the memory is either zeroed or it's not zeroed, right? It's the controllers left up to the person calling this stack initialize. So it's flexible in that way. It doesn't happen for everything. So the next thing is to actually finish this deallocation one. So you want to say core dealloc, pass in the allocator, then pass in the stack data, stack capacity times element size, and then element align. Now, it's probably good if we zero this because we might want to reinitialize it maybe. And then it's not pointing to some memory that was already, that is possibly being used for something else. Awesome. Resizing. So resizing is something where, it just changes the count. Okay, so we essentially just want to do a core debug assert for, and we've got this array resize thing. So this is really nice. We can say, what do we want to resize it to? What is the capacity? It does the check already. It's only in debug builds and gives you a nice error to say, hey, cannot resize array to this count when the capacity is this guy. So that'll show up. It'll do a stack trace, all the bells and whistles, super nice. So we just want to say stack count and then stack cap. So that already does the check for us in debug builds, but in release won't do it. Then, wait a minute, sorry. New count, resize into the new count. We don't actually need anything because all we're doing is very simple. It's just setting the count to new count. So obviously you shrink it, it's safe, but if you extend it, it's either uninitialized or zeroed memory. The controller's left up to the person. We don't want to do anything complicated. We don't want to pre-initialize it. If the person wants to zero it, maybe we can say resize 0, and if we really want to use it a lot, we can add a new function to say resize zeroed, and it will zero it if it extends. But yeah, that's something to to add if we actually need it. So we don't actually need this element size and align. So we're going to remove that because it's just a waste. And we're probably getting lines anyway because it's so small. But yeah, push many. So ultimately what we need to return is some form of so we could literally just do here's the pointer, and this is going to be, so we could return the old count, right? That would be nice, wouldn't it? Let's return the old count because that might be useful. And then we want to, we could just use this resize thing. Yeah, let's just use this resize thing. We could just do it inlined. Yeah, let's just do it inlined manually. It's not rocket science, right? I guess we could pass in a boolean to say if you want to zero it or not. That's also a thing that can happen. But yeah, and again. So the new count will be stack count plus amount. We'll get the current pointer. So we'll say, we'll get the new sort of, where's the element's going to go? So I guess we'll call it pointer, not a good name. So this will be core pointer add, and this will be stack count. Wait, do we not have the initialize thing? Let's put that there. Good. Stack count plus amount times, oh no, sorry, not plus amount, multiplied by the element size. There we go. I don't think we need the align. Probably for a lot of things we don't need the align. I'll think about that. So, this could just be a resize. But yeah, let's just do. So we say new count equals that plus that. Assert the resize. put it there, return the pointer, and then they can start writing over that. Conflicting types, let's sort that out. So maybe we can get rid of this type of. That'd be interesting. If, maybe we make you only require T here or something. I don't know. We'll see. Because we only need it for initialize and deinitialize, potentially. Pop many. So popping is, so push pushes on the end, pop reduces from the end. So we probably want to assert that we want to do an assert to say debug assert that amount is less than or equal to the count, right? And then you're going to say popping ZU okay, we say like stack has this many elements, but you are popping this many elements off. Off the end or something. So then you will just pass in stack count, and then you'll also pass in the amount. There you go. And then you simply just say stack count minus equal amount. Obviously that will underflow in release, but we tried. We could put an extra if statement in. We could max it, right? Max the element, but cool. So again, we don't need this size and align. So for pop, we don't need size and align. And then for insert, we only need element size. We don't need element align. For remove, we need the size because there's a copy involved, right? So the align isn't really needed. It's interesting. Okay, so we can remove a lot of those as we go. So insert, we only need the size, right? So how do we insert into an array? Well, remember if you have more arrays, let's draw them. So you have an array of elements or whatever. Okay, you want to insert your element here into slot index 2. So what you need to do is you need to copy these ones over by 1, or over by how many you're copying, how many you're inserting, and then you can give back a pointer to this, and then the user can overwrite it. Okay. So what I want to do then is simply, so for that use memmove. So you could use memcopy nowadays because memcopy basically uses memmove, but just to be more explicit about it, I guess. So what you need to do, there's it's like memcopy, destination and source. So what you need to do is say, I think there needs to be an if statement, because what happens if the stack, So if your index is +1, oh wait, so we need to do a check. Debug assert array bounds, yeah? So it'll be index with stack capacity. Then you want to say, okay, if this is equal to the stack count, right? Meaning you're saying insert at the end of the array. That one. If you're saying insert at the end of the array, you basically just do a push, right? Whereas if not, so you probably want to say this less than. This one will do the mem move, and this one will just do a push. So we'll figure this out. Let's do the complicated one first. So basically we need an insert pointer. So that'll be index times element size. And there we go. That's where it's going to go. So we need, so the destination, so you're copying, say if you're inserting one element, your destination of where they start is one after, right? Because you're inserting one element. Oh, there's an amount, isn't there? Shoot. Plus amount. So it's 1 by default, and you can't push 0. Well, you can push 0. If they push 0... I have to leave. It's midnight here. See you next time. Awesome, Rohan. Good to see you. Thank you for the sub, by the way. Appreciate it. Hope you have a good rest of your week. And yeah, perhaps see you Sunday. So the amount... Yeah. So what happens if the amount is 0? We didn't check this in the push before, right? So if you push 0, it just gives you the end of the array back. And you would have pushed, you might write to that pointer and it's wrong. So pushing on nothing is probably an assertion. Non-zero. There we go. Non-zero, please. Well, no, you can you can pop 0. It doesn't matter. Does nothing. But inserting 0, that's a problem. So you do that plus count amount. That's fine. Yep. Okay. So now what you need to do is, so your destination pointer is this, whatever the pointer is that you got, plus the amount times the element size, right? So that gets you the pointer, that gets you the destination place where it's copying to. And then you need to pass in the pointer because that's the source place it's copying from. And then the amount you're copying is essential. Now this is where, you got to think about it. So you're copying the amount that's left in the array, okay, count, minus the amount that we're pushing in. And it might be a -1, so we have to think about this. And then it'll be times the size, right? So let's think about this, right? So if you're pushing 1 on, so here's the easiest way to check. So if we have an array of elements and we push onto, this is the end one, right? Or the one before the end. And we want to copy. So we stack count. So this is 1, 2, 3, 4, 5, 6. So it's 6, take away 1. That's wrong, isn't it? Because that's saying copy 5. That's not right. We need to copy where this. So index plus amount. So that will give us, so 0, 1, 2, 3, 4. So that's 4 plus 1, 5. And then we're saying 6 take 5. And that's one element we're copying. Good. Times element size. That's it. So that's the code. So let's try it for 2, make sure we got it right. So we want to say, so we try it here. Let's say we're copying 2 elements. Or let's say we're inserting 1. Yeah, let's say we're inserting 1 element. So the stack count is 6. The index is 3, right? Or 0, 1, 2, 3. Yep. So it's 3 plus 1, so that's 4. 6 take 4. Okay. That gives me 2. So I'm copying this one. Oh, is that wrong? This one and this one over by 1, and that's right, because you're creating a new slot, right? Yep. So we just need to make sure, so you're resizing it, right? Make sure that index is within +1, and then we need to be able to do a resize. And the resizing the index plus amount. Index plus amount, make sure that's within the capacity. Yes. Excellent. So yeah, it gets a little bit complicated when you do this, but you just got to think through it, right? You know. But yeah, it's kind of, you know, if you're a beginner, this might be a bit confusing. But yeah, you should really write some tests. But we're just going to let our code be the test, and we're just not going to change it. Oak Spirit. Anyone know any good resources to learn the system APIs for things like window creation, drawing, textures, keyboard input? I've used an SDL2, but I have no idea how to make something like by myself. Yeah, he means by Win32 API. Yeah. Yeah, Oak Spirit. So I'm going to plug myself for a minute. We did this all from scratch, right? And there's a VOD channel. You can literally watch it all. There's... actually, no, we've not got to the keyboard input yet. We've done creating a window. But yeah, we're going to be doing keyboard input very soon. But yeah, I also recommend checking out Handmade Hero. I'm giving you like proper Gen Z resources, you know, videos. Like the first like 50 episodes of Handmade Hero, probably what you're looking for. Right. Where's the YouTube channel? Complete, that's it. Right. What else? Other than that, you can read the SDL source code and figure out how they do it and make your own version based on seeing the calls they call, right? Because sometimes it's hard to figure out, like find the exact API. So it's just good to see how someone else has done it and then look at the APIs and implement it. Because some of these APIs are really old and they're not great. They've not aged well. So doing raw Win32 and X11 code sometimes isn't that nice. Awesome. Yeah, so just read source code and check out videos. That's my recommendations. There are probably tutorials online. Just search around on Google. I'm not sure if there's any good blogs though that I know about. But yeah, that's all I have to say on that one. Stack count plus equal amount. Yeah, we'll pre-add it, right? Right, so that would have pushed, so we can return pointer. So I think that's done everything, right? It's doing the copy, if it needs to do the copy. It's calling into memmove, it needs to call into memmove. Yeah, I should really test this, but I'm not going to test it until I actually do it, until I actually use it, and then I'll give it a bit of a play. But yeah, you should really have, test out this code that you write. Test out, like we know where the problems can surface, right? There's an if statement here. So before the end of the array or at the end of the array, we can push single or many. So there's things to test out, right? Memmove, awesome. If not, do you just do nothing? You get the pointer, which will be at the count, right? You increment that, and you probably just do nothing. That's it. So there's the insert. So again, insert and shift remove, they're a bit of a pain with this memmove, but just think through it. You can sort it out. Space Goblin, how you doing? Or Render Goblin. You've taken a new form. Excellent. Right, next one. So to remove. Is basically like the pop, right? So when we say resize, what we're kind of saying is, well, because it's an unsigned integer anyway, this could really be resize. And that would just be new count, just be takeaway instead, or underflow, Excellent. So really, when we talk about right, so we make sure, why is that a +1? Oh, yes, +1 because, yeah, good. Because you can insert, right, so you want to pick an element, actually pick an element to remove. Excellent. Yop. Wait a minute, is that right? Index plus amount. If the amount is... Wait, maybe this is wrong. I don't think it's plus amount, because if you say index +2 and you go above, you're just going to overwrite stuff. Right, it just needs to be index. If index +1 is less than, yeah, that's good. Then you need to shift all the stuff that comes after. Right, so for the remove, this is a shift remove, so we just shift the other way. So for this one, you kind of don't need the pointer unless you're in here. Get a new count, fantastic. Now, the idea is if the index plus the amount, right? Is that right? Index plus the amount. Yeah, if the index plus... So this one needs to make sure that... Yeah, because that can go all the way to the end, basically. Yeah. Because if you're removing the whole of the end of the array back to some certain point, it's not a shift anymore, right? It's just you just change the count and that's it. It's just a resize. Whereas if not, you actually need to do a copy. So should you call it DST? That's source, actually, yeah. So this one is going to be, so you're going back. So your DST is going to be based on source plus it might be the same thing. Is that right? I don't know. Let's put it in there and work it out. And then it will simply be, wait a minute. It was amount, wasn't it? Yep. So it would be destination source. Right. Let's do, so this is the last painful one to do. The others are just really easy. The other ones are really, they don't do mem move. So destination. Hey, you're doing well, thank you for asking. I'm a bit being slack and hook into playing Black Desert again. Nice. Cool. Awesome. Good to hear. Yeah, it's good to take breaks and play some video games, you know. Get some ideas and relax. So say if we are here, we want to remove this element and we want to remove 2. So we want to remove, well, sorry, let's say we want to remove, 2. We want to remove this one. No, so, right, let's just, let's say remove 2. So remember it's 6 in size, ignoring this extra one we've just added on. Right, there we go. So we want to add, okay. This one, we want to remove. So what we need to do is we need to say if this plus amount, so we're saying plus 1, because just removing 1. If this, so this is 4, right, this is less than 0, 1, 2, 3, 4. It's less than 6. So is it amount plus 1? So, because if we were here, you would want to do 4 plus 1 plus another 1. Yep. That means you don't... Wait a minute. No, that's still wrong. Right. So if you were here on 5, plus 1 gives you 6. Okay, sorry. So that means you don't have to mem move, you just change the size, right? You just reduce the size, and then this is gone. So in this case, we got this right. So the source is going to be this thing here, this arrow here. And the destination is going to be this. Oh no, this is the destination. The wrong way around. Then the source that we're copying from, so it will be this plus the amount. So it'll land you here. and then you're copying the counts, that's 6. Index plus amount, so that's 3, that's 4. That's 2. So you're copying this one and this one back by 1. Excellent. That's it. Cool. So that's the shift remove. All sorted out. I should probably do a double check on the insert at some point, or maybe just test it out, you know. But yeah, I think I'm pretty happy with those. So the swap remove is we're just swapping the current one we're looking at, and I forgot the index. I need to remove those lines, isn't it? I forgot to put the index here. This is not good. Come on. Okay. Excellent. So how do you do a swap remove? So you're just swapping, yeah, I guess this one might be, yeah, this has actually got another mem move in it, damn it. Right. So say if you're doing this one, say if you're swapping one element, you say this plus, it's the same thing, the same check. The thing is though, is the source pointer is different. So you're copying, is it the right? Yeah, the source pointer is from the back. So it's stack count take index, something like this, plus amount. I think it's that. I'm not sure. So let's run through it. So the destination is going to be, so we're removing this one element. And the way we're going to do it is we're going to copy this element at the end of the array to here. And then we're going to reduce the count on the, we're going to reduce the count, right? So, oh, it's just minus amount. Sorry, I was being super silly. Right, so this one is destination. The source pointer is the end of the array. So it's count, which is 6, take 1. That lands you here. Then you're copying one element, right? So no longer are you copying many elements, you're copying the amount, right? You're only copying the amount. So this is getting copied to here, and then we reduce the count, right? Awesome. So if we do that multiple, so we did 2, right? Now this is where we've got to be careful, because there could be a bit of an overlap. So say we're removing these 2. Then this, so it'd be index plus amount. And that will be, yeah, 2 plus 2, so obviously 4, right? So that lands you. So is 4 less than 6? Yes, it is. That's fine. So we're going to take 6, take 2, take these 2, and then copy it on top of here. So that works out fine, but we got a problem. Because we didn't do plus, so we wanted to do plus 3. So we do plus 3, then we get an issue of, so it'll be index plus 3, so that's 2 plus 3 equal 5. And then you're copying this one element back here. So if you're copying, there's 2 problems. Or is it just one? I think you just need to min the amount, something like that. You min the amount with the remaining size or something. So this gets copied. You ideally want this to be there, right? So the destination pointer is here, right where the pointer is. The source pointer is count take amount. So it's this take 3. That's incredibly wrong. So in this case, the amount that we're copying needs to be, so the problem is, see, I've done this before, but I want to figure this out, and I'm tired. So yeah, let's see if we can do this. So, like, without looking at anything. So we're moving this back here. We've got an index of 2 and an end index of 3. And ideally, the difference between the end index and the end of the array is less. Right, so what you want to do is get like some form of like end index, I reckon. And that is this. And then you want to say, okay, given the end index stack count take away end index, so given the amount from end, right, this left, you want the amount to be the core min of amount with amount from end. Okay, so that will reduce to 1, because if your index is 5 and you've got a count of 6, that will be 1, and then you min it, and then you're saying your source pointer is 1 from the end, and the amount you're copying is just 1. Excellent. So we fixed that problem. Now, is this issue going to show up? So I'm going to check to see if I've done that in the past. I know I've done it. It feels like I've done that in the past, but I want to just quickly check. Is that the same problem with the shift remove? So if you're shift removing 3, so if you're shift removing 3 elements, so what you're going to be doing is copying. So when you shift remove in this case, it's actually going to be the same. So we'll follow it through. Index plus amount. So it's index plus, yeah, so that's obviously 5, right? 5, it's less than 6. Woohoo. So it's got to do a mem move. So it's destination, right, this guy here. Source is destination plus amount. So 1, 2, 3. Then the count is this wacky thing here. So it's index plus amount. So that is 5, right? 6 take 5, so that's 1, right? And then you're copying 1 back to there. And then you're reducing the count by 3, meaning 1, 2, and 3 are taken off, and voila. So that's good. So those are both great. So let's check the implementation of what we had before. Oh no. I tried my best not to. Hey Meeple1, how you doing? I hope you're enjoying my drawing skills. I can only draw boxes and apparently those things. But yeah. Yeah, I'm doing good. I'm a little bit ill. I got a bit of a sore throat. And been a bit drained because I drank too much caffeine. I've twitched my eyes to the left fast and right. I feel the muscles in my eyes, a bit strained, and this part of my face was very, but yeah, other than that, doing super good. Really enjoying stuff that's going on. Super happy with lots of things. Hey very much, how you doing? How's things going? You're just in time for the awesome stack. It is almost completed. So what was it? Remove swap. Okay, I did it without an if statement here. And the reason why I did it without an if statement is because you pass in 0 into memmove. But yeah. So this is an old version that I've done. So we did destination So source index is count minus the amount. Sorry, no, we reduce the count there. Then we min it. Yeah, there's a min. We see a min. So amount from end. So that take the end index. Interesting. So we took the amount off. Right, which one is better? They're basically the same, isn't it? But I stored it in this pointer, but it's, you know, because we're just calculating that. Yeah, they both work the same apparently, it's just different ways of doing it. Yeah, so this one is instead if the new count, right, new count, min that new count with the amount. So we've got a new count up there, meaning we could just use that. Min the new count with the amount. So if the new count ends up being, is that right? Oh, then I would do header count take amount. Yeah, that's what I do, header count take amount. Excellent. So, yeah, this one is probably better. See, past me was better at this apparently. Past me is more advanced. So accumulate that knowledge, people. How do you swap remove from a stack? Do you not have differently sized allocations from the stack? So stack as in just it's the dynamic array, right? So do you not have different sized allocations from the stack? So we only allocate our growable array when we initialize it, and we just have a count that we move, a count cursor that we move. So there's a count and a capacity. Yeah, it's a dynamic array. You know, because the way that people usually uses like vector, and then array just kind of seems like a C array. So I just use the word stack because you kind of should use it in a stack fashion, right? But yeah. Yeah, it's just my name for it. So let's run through that again. Destination, right? That's the index. Destination. The amount we're pushing, or that we're removing, is 3, right? So we're saying the new count after this will be 6 take 3. 1, so obviously that's 3, right? So then we want to min 3. Something is wrong. This isn't right. Source index. Wait, no, where's the mem move? Amount. Huh? How did this work? Did this work? Did this one work? Amount take... So the new count would be 3. So you're saying 6 take 3, you're copying... Right. Yes, you're adding 3. Right, so 1, 2, 3. Excellent, goes on to the end. Now the amount you're copying is not amount. I think the other one was wrong. Yeah, that was maybe copying more memory than it should have. Alright, let's undo it. Right, so past me was not as good as me. That's what we've just discovered, apparently. Right, past me is inferior. Good. Right. Much better. Also have dynamic stack, which is fast temp memory allocations. Awesome. Yeah, so the problem is the word stack is overloaded, right? There's a stack data structure, and then you have the call stack, right? So whenever whenever I try and refer to the stack, I don't do this well, but I should really call it the call stack, right? Or there is a stack allocator, right? But I guess I'll be explicit about the name. I'll call it a stack allocator. Yeah. I see what you're saying though. But yeah, I know you're a fan of the short names, Right, so pushing on a string on the end. This one is very similar to... Huh. So you're pushing on a pre-made string. Yeah, so this is simply just core stack push many. Right, we're passing in stack. Do you want to point it to stack? Point it to stack, please. Then what I want is we're pushing on, where's the push? Push many, it's just a mount, string.size, and then we get back the new pointer, so that's char star destination, then it's memcopy dst string.data is the source, then we're saying string.size, then we're simply just returning a new string, core string, destination, and string.size. Cool. The next one is the format thing that we did before. So we're going to grab that. The one that we did up here, right? This one. So it's simply just, it does it into the stack. So this one would be, this one would then allocate it from this, so it'd be like a core push, stack push string, stack string. Wait, we've already got this. No, we're not pushing a string. We're just doing a push many. Stack size. Size goes there, then we're going to put it into there. Excellent. So we do that same trick, right? We do the sn printf, get the size. Oh, I think we've got to do size plus 1, because we need to allocate enough for the null terminator. Ooh, we forgot about that. Should we do that? So size is that plus 1. And then we probably want to not include the null terminator in the size, maybe. No, I think we'll include the null terminator in the size. Yeah, we'll do that. So it's this plus 1 for null terminator. Excellent. Right, and then we just do that same thing we just did up there, which is just effectively this, where we can, have the easy, the proper variable args, and this is, if you already have it in a VA list already, you can use this one. So that's just going to be this there with stack and args. Voila. There we go. So that's our stack implemented. We should take a look at this. Stack is a reference that allocation sizes are calculated at runtime. I suppose using the stack of your thread, where you need to know the sizes at compile time. Yeah. You want to avoid using alloc A. The problem with alloc A is that it doesn't fail nicely, and you have to know it at compile time, and you don't know the size of your stack in every function, because the same function could be called on different threads, and the threads can have different sizes. So yeah, basically just having like a custom allocator, which so we've kind of implemented a stack allocator in a way, but we'll call it a linear allocator. But it's more of like a manual stack, right? So it has like a start cursor and a start and an end, right? So that this is the allocation. There's the end of the allocation. We initialize it and allocate from the OS, and then we just bump the cursor every time we allocate something. Now, this linear allocator has a way to get the cursor and then restore the cursor back. So you can think of it as a stack, right? But you have to manually do the stack. So the thing is about a stack allocator is you typically have to deallocate in order. And if you don't deallocate in order, you might get problems. But maybe you can put some assertions, or you can put some if statements in just to ignore it. Why allocate is probably anything unprofessive if possible. Yeah, because it's all unsafe, isn't it, in Rust? And the default classes are all not really built with allocators in mind, are they? They've got like a global allocator, isn't it? Just a bit of a shame. So we could get rid of this type of here, right? Should we get rid of the type of? Because I bet you if I compile this, it just makes the API just a little bit annoying. So let's go to core 82. Core pointer add. So I thought I had pedantic on, and pedantic should have avoided. I thought I had pedantic on, you know? Wait a minute. GNU 11, so it supports some extensions. Then maybe, but I got pedantic, so I don't know. Oh well. Anyway, so I think, you know, we'll keep it. Worst case is we'll remove this type of here. But we need it for a line of, because you can't do a line of expression even though compilers could do it nowadays, because it's all implemented with like a built-in. But the C standard doesn't support it, so they didn't do it. It's really annoying. So you have to do type of, and this is coming in C23, but it is a GNU extension. So we're kind of using it. I would prefer not to. But yeah, because I'm thinking we're only using it in 2 places, we could just pass in type T here. But then if you get that type T wrong, there's a problem. So we could have like a static assert here to check to make sure the types are the same. With an optional type of, and it only compiles properly on one compiler, but then it's the same problem again, right? So it's weird. Yeah, C doesn't have the necessary generic fancies and Rust. I'm not sure, you don't need generic fancies. Like we just did it all without generics. Like this is all type safe, except for, you know, it's using one extension, but it's all type safe. Using nothing but legal C without generics. Non-pod types. Oh no. Yeah, pod is amazing. Like non-pod just adds so much complication. I feel like comparison, I just expect memory safety from Rust, which is precisely the reason why it's different. The problem is it's easier to solve when there's... The problem with pod is or anything that's non-pod is there's implicit behavior in your program, and you have to be a wizard of everything. And what else? Like, then you have to really understand what your superclass does, right? And you really have to study it a lot more. Well, you don't lose encapsulation, right? That's not bad. The problem is encapsulation that's enforced is bad, right? Because what happens if you just need to ship something and get something done, and you can make that change to the thing that you need to make, and not have to fight a compiler error when the memory is just there. Like, because this is available, we're not saying use it. We say, you know, like we provide a public interface for ways to get things. You know, we should really do that actually. Provide a public interface for count and stack. Actually, I forgot that one. So this would mean that we've got some form of public interface that they should use. But if they want to get access to the underpinnings, they can do that, right? You know? And I find that really, like, I remember using Rust, and there was a trait that was implemented internally in the standard library, and it was like a two-string thing, but it wasn't implemented publicly. And I couldn't turn it into a string without writing my own, all because they kept it behind some encapsulated thing, but it was all declared in the same place. So yeah, it's a real problem. Obviously in C you still get encapsulation with compilation units and things like this, but I like to include always an internal header so people get access to the internals if need be, you know. But yeah, you can always place global allocator both alloc and free with size and line. Oh wait, what am I missing? Oh, the global allocator. Yeah, yes, right. Yeah. Global allocator, yes, as well as pointed to in the nightly build, right? Rust nightly, yeah, forever nightly, yeah. Better use encapsulation. C++, yeah. People rely on public access, and before you know it, you cannot change the API because people rely on the public access too much. Yeah. Yeah. But like, you know, people can always, you know, do an unsafe thing in Rust and get access to your data, right? They can still do it. It's just a pain. But yeah, good chat. Good chat. Yeah, so this is cool. Should we try this thing out? Right. So we're just gonna go into the main file, and we're gonna have a bit of a play. We're gonna say, right, core stack of U32. Here's my integers. And it's gonna say core stack initialize address of integers. How many integers we have? We can have like 4, because then we can make this thing error. And then we're gonna say, wait, what else do we need? Oh, the allocator, of course. So we need a linear allocator as well. Core linear allocator, and we have a linear allocator of allocator initialize address of that guy, please. And we want to allocate, let's say, 4 megabytes. Core megabyte 4. So we have the allocator. We can then use that super lovely, you know, we can say core linear allocator, take the address of linear. So this is our allocator interface. We've got 4 of those guys, bam. Can I take the address of R value? Right, so what's going on there? Good old R values. I like me good R value. So obviously all of this is crap. So sort all that out. Forgot to wrap it in the brackets. Macros for the win. Oh, see. Don't we love this? And you don't tell until you compile it and use it. It's just amazing. Ugh. And we're there. Right. So Bam. Compiles. So let's stick a beautiful core breakpoint, and if we reach the trap, it's fine. Right. Roll the memes. So is not initialized. So we do a thing where you should really zero it, you know. Is that going to get annoying? Probably. But then, yeah, I think that's going to get annoying. So, you know, let's remove it. We might, yeah, I just feel like that's going to get annoying. So let's try that again. Right, so we hit the trap. Thank you, Akbar. It's a trap. So now we just want to do a couple of pushes. So if we push 5 times, let's see if it crashes. We should hit the out of memory handler. You know, but we cannot tell because it'll hit the assert. You know, I don't need that breakpoint there. That was a dumb idea. Just do it out of memory, right? Let's do a push. We're gonna do a deref. We're gonna push 1, 2, 3, 4. So it's literally just like this. 1, 2, 3, 4, and then we'll push a 5th one on just to make it crash. And says the crash cannot resize array 5 with a capacity of 4. And then if you do this, we also want to be able to say, right, printf this thing like that. So I want to be able to say integers. Well, so you know, really should use the, you know, you should use the getter because then you get bounds checking. Something got buggered up. So if debug assertions. Huh. What's the error? See if we get a more sane error in here. So the sane error is member reference, blah, goes through, land there. Condition. Condition is index count. Index count is that. We didn't take the address. Right, that's not really readable, is it? We could make it into a function. If we make it into a function, it'll be readable, more readable. If we make a function, it'll be more readable when there's a problem. If not, it just goes through too many macros, you know? Yeah, think about that. That compiles, give it a run, print out 1, and then we've got a trap. So that's because we didn't print out all 4 of them. So let's do 1, 2, and 3. Obviously, it's only testing push. There we go. Let's insert at index 1. So that should insert 3 before 2. 3 has gone before 2, then 0 is there. Why is 0 there? That seems a bit wrong, doesn't it? Gotta have a look into that. So you insert, yeah, so I think it's just one too many copies. So should we put breakpoint in and find out? Core breakpoint, let's move that up. Right, let's hop in. So we've got new count of 3. Right, we're inserting into... So the index we're inserting at is 1. And it didn't do a copy. Because index is 1, it's got size of 2. So new count is going to be 3, right? Yes. So we insert a 1, it should be inserting before 2. So maybe it should be if index is less than... So if index is less than... So it'd be 1, there's 2 entries. So if index is less than 2, we do index plus, so 1 plus 1, 2, 2 take 2, so you're copying 0. There needs to be a plus 1 in here. Or you need to be using new count. Is that right? No, not new count. Is that what we did before? Have a look at what we did before. So we get the count, it's count take index. Oh, it's just count take index. Yeah, maybe I'm just doing that too complicated. So we count take. Yeah, but maybe that could be wrong. It could be count take index. Let's give that a go. Right, so see what we get. 1 3 2 4. So that's what we expect. Good. So if we insert 2, that should still work, right? But it shouldn't do any copies. Yeah, but it won't do any copies. Hopefully, right? So let's put another core breakpoint in there. Just to quickly have a little look. Do a GF. So it shouldn't go into this if statement. It doesn't. Excellent. Cool. So we can try that again. This time we can insert 2, but we're going to leave out inserting anything. And the memory will be zeroed. Okay. So this time we're going to insert at 0. We're going to push insert many. We're going to insert at 0 2 elements. We'll just push a 3 on. 3 will go at start, 0 will go second, and it should copy the 2 over. Where can I watch day 1 from? Yes, we have a VOD channel. But if you want to have more of a high-level overview, we also have a YouTube channel where there's 2 devlogs, so you can see what this project is about, why we're doing it. And the second one is, wait, we've done 3 now. The project structure that we got in the end, and then also the GPU API is completed. No worries. Let's see how that looks. Let's remove the trap. So we've got a surgeon on push many. Oh, because we said 1 too many, right? So let's up that to 5 now. And we are actually going to print out another one. So 3, 2. Wait, why is there a 2? Dun dun dun. So I think the copy is a bit wrong there. No. The 2 is fine. Because it copied 1 and 2. So we pushed on 2 elements. It copied 1 and 2 here. And then we only set 3, right? Excellent. That's good. Cool. So let's insert 3 elements. And if we insert 3, see what happens. So we're resizing to a count of 6 when we have a capacity of 5. Right. I keep doing that. Three, 2, 0. Right, that makes sense, right? Because right, we've got to see how much it's copying. So when you do so you put 1 and 2 on, they'll be in 0 and 1 in the indices in the stack. And then you go back to the start, you push 3 on. And because you've pushed 3, you need to copy 2 elements after where you're inserting, right? So, oh, thank you, TCAP. Thank you so much for the raid. Appreciate it. How did the stream go? Welcome, raiders. Yeah, working on a game about an engine. We've just done the custom allocator stuff today and our custom growable array, which is the stack. If you have any questions, please ask. Ask away. Awesome, good to hear. Thank you for the raid. Appreciate it. CryoCan, thank you for another sub. Appreciate it, my friend. Thank you. So all the subscribers, if you go onto the Discord, you can get access to the code straight when I push it up. So I'll just leave a link there in the chat. So if someone subs or if they've support via Ko-Fi, which is nicer for me, yeah, you get access to the code. So thank you for that. Cool. So 3, 2, 0. Yeah, so we move 1 and 2 after the 3 we insert at the beginning, and then we insert 3. 2 stays there because it was a mem copy and we didn't set anything, right? They're uninitialized memory. And then we get 0 there because the whole memory buffer is zeroed, like because it's using virtual memory. And then, so that's got a 0 there, yep. And then we put 1 and 2 after that, and then 4 gets added after the insert, right? Ta-da! That's really nice. So let's check the code and make sure it actually works, right? Because we want to see like the numbers, right? Make sure it's all good. So it does the move, but the move needs to be 2. It is moving 2. It's good. Excellent. Awesome. Right, happy about that. So we've got the insert and push working. Pop will be working, right? It's basic. We've got the swap remove and the remove to look at. So if you were to have just a linear set of numbers, so if you go from 2, 3, 4, 5, and 6, yup, you could then do a swap remove, swap. So you'll swap remove, let's do a many. Swap remove from index 3. Doesn't do anything. So index 3 is obviously 4. Right, where are we removing from? Good point. So we're going to move from 0. I'm going to swap remove 3 elements. So 4, 5, 6. So we did 1, 2, 3, 4, 5, 6, and then we moved 4, 5, 6, which are the last 3, back to the front. So yes. So what happens if we remove 4? Does it complain? Yeah, that'll be fine, but it only gives you 2. So let's see how that one behaved. Because it should have done a min on that, right? Let's just have a bit of a gander. So what we should see is, because you're removing more than there is elements left at the end that you're swap removing, the end index should be 4, and you do a difference, which is 2, and then you min that with the amount, which is 4, right? And then it does that. Good. Then does the mem move appropriately? Very nice. Very nice. We also didn't test, let's say 2, well, from index 4, which is 5, and we're going to remove 2. That should work. Right, let's remove the breakpoint. Oh, come on. Wrong one. Yeah, so we just removed the end off, right? So that's 5 and 6. We've popped those off. But that shouldn't have done anything. That should have just reduced the count, right? Yep, just reduces the count, doesn't do a mem move. Nice. Right, one more thing. If we say 3, that shouldn't work, right? You shouldn't be able to remove 3 because you shouldn't be able to remove 3 elements, because if you can remove 3, you go off the end of the array, right? Because you just start at 4, 3. But I guess it would do a clamp, or it does like a min, right? So maybe that's fine. But what we want to say is like, hey, make sure this is in bounds, and the end index, which is that plus amount. If that plus amount it's got to be not really indexable, but I think that's right. So we do the check. Three is outside of main 4.9. No, it's not it. Oh, I did it on the insert. Don't mind me. And the remove. Right, so 7 in that bounds of array of 7. But it's not really got an array count of 7, has it? If we reduce that number, yeah, the error for that is not really the best. Like yeah, so ideally you want to say that plus that take 1. That's it. That'd be the better error. And then you say 3, right? Cool. Hey there, Blowfish. How you doing? Welcome, welcome. Friends of the iterator skip removed. Interesting. Yeah, so iterator skip remove. Maybe. Right, you can swap it. Or, yeah. Nice. 6. Nice one. So we should be able to put that on 2 and that'll work. Oh yeah. There you go. So that's the basic tests done, right? We just fixed a bunch of bugs. So we've got these linear allocators now, and we also have the stack. So what I'm gonna do is I'm gonna push this up, and so next stream, let's go to see what's in for the like what's after this. So ideally, a growable array is not the only thing that you want, right? Ideally, what you also want is a you probably want a hash table. You probably want a hash table, and we probably also want an object pool. I could get a double-ended queue in as well. I'm not sure. I think I need the double-ended queue for events, basically, to pull an event off a queue. So I'll probably do a double-ended queue actually. But yeah, so next stream we'll get a double-ended queue in. Implementing that from scratch, that'll be difficult. It won't be difficult. There'll be one part of it where I have to go and grab the old code because it's a bit weird to remember. But yeah, then a hash table, like, hopefully you should minimize when you use a hash table. There are only really a few places you really need a hash table. Because sometimes just a growable array is just as good as a hash table, if it's very small. But we definitely want to have one in because then we can just start using it. And then we also want an object pool as well. So this is like a quick way. So you basically just have an array of elements, and the array can have holes in. You can deallocate and allocate individual elements in that array super quick. And yeah, it has its pros and cons, but it's something I use pretty much everywhere. And then with this, we have all of the collections that we'll need to actually do some keyboard and, well, just do some input right from the keyboard and the gamepad, and do stuff like hotcode reloading and a custom UI. So this is the plan. Let's get this up on the, let's just give it a run. Awesome. So this should just work on Windows because we've done nothing different, except for if the virtual memory stuff just doesn't work. So I'll probably give that a bit of a check. So if we do a status quickly, see what we got. Do a git commit -a. So we've added a custom, allocator interface, linear allocator, and a stack, a growable array stack. Ooh, right, and a stack implementation. Excellent. Let's see here. Thank you for the follows, appreciate it. So let's do the bash dance. I don't know why I have to keep doing this. Keep failing it. Trying to fix it. Super secret password. Now I can do a git push. Then I want to do a new tag for day 11. Come on. Work with me. There we go. I don't know why it took so long, but git. So let's do a nice tag. We're going to say day 11. And then we're going to say git push all the tags, please. So yeah, for those who have access to the code, you can go and check that out and have a bit of a play. Awesome. Right, so the next stream will be on Sunday, 4 p.m. GMT +1. There's a Discord if you want to hang around in the meantime, ask questions. It's all here. Tons of stuff. But yeah. This also will go up on YouTube as well for people who want to watch it, or you can just check out the VOD on Twitch for 2 weeks if you want to see the stuff that happened before. But yeah, thank you so much for coming, everyone. I'll hope you all have a good rest of your week and weekend. I'll see you all on Sunday. Let's find someone to raid. Hopefully, right? People exist. Every time, Kanji, watch it. Why? See, Kanji used to stream C typically. Sometimes he does JavaScript for some reason, but he just streams himself like this. How is it practical? Why? Thank you. Yeah, it was really fun doing the stream today. It was awesome. We did a lot. We did custom allocator interface, linear allocators, and a stack, and we tested it all out. Pretty decent progress, all in about 4 hours. So that was decent. Well, less than 4 hours. But yeah, I cannot raid Kanji because that is just... I don't know why he bothers streaming that. Let's raid TJ. Is TJ trying to raid someone else? Look at this. He's offline now. Yeah, classic. Yeah, thank you on the closure. Appreciate it. Right, let's go hunting. It's rabbit season. Let's see if we can find anyone. And why don't they just give me what I want? Maybe because I haven't followed it, but still, it used to be there. And then they changed their code. Clearly. Software and game development. Looking for the C's and the PP's. So he says open jail, but it's got Vulkan in the title. Whoa. We can raid this giant guy. There's a rust guy. Do 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 do. Yeah, I cannot see any C's, which is fine. I guess I'll be the only person who streams C, but yeah, if you guys do any C programming, start streaming. It's a good way to learn and also focus. Highly recommend. And also get better at speaking, because I used to be terrible. Right, have a good... Anyway. Yeah, enjoy the next stream, guys. See you later. Thank you for coming. Really appreciate it. And yeah, see you in a future one.